I gotta figure out a way to make it like, I don't want to say mandatory, but I and also I also have to figure out a way to like delete videos in mass because it's like click on the three dots, scroll down to delete, hit delete. Click on the three dots, scroll down to delete, hit delete. And it's like it took forever. It was very annoying because there's like hundreds of videos that have 0 views. I'm like, why am I even doing this? And so all the linear algebra ones from like this course, I was like, you know what? I'll give the benefit of the doubt. That one I only posted up 2 days ago. So yeah, there's no hits on that one because we haven't taken the test yet. You're not prepping for a test, so you're not motivated to go back and look at it. Or I did such a great job of explaining it in class that you don't need to. But yeah, I got to stay on top of deleting that stuff. Uh, Also, I'm starting to think I don't even need to record it. Make my life a lot easier. Anyway, so the trace of an n by n square matrix is defined as the sum of the elements on the main diagonal, right? So, so yeah, more on that later. More on everything later. I promise there will be a payoff. It's actually pretty cool. So we have the sum of the eigenvalues equals the trace of A. Whoa. All right. And the product of the eigenvalues would be the determinant of A. Right? So let us investigate. And also, it doesn't hurt to do an eigenvalue, eigenvector kind of situation with a 3x3 matrix just for practice. So lambda I, oops. A minus I lambda, or lambda I, doesn't matter. Commutative property. Well, it's a scalar multiply. So negative lambda 1, 2, 2, 3 minus lambda 0, 0, 4, 5 minus lambda. Again, I like doing it this way, just like in the last one. I like using the A minus lambda I because on the main diagonal, that's the only thing that's going to be impacted by the calculations here. For a 2x2 matrix, not challenging really, either way. But the bigger the matrix, the more complicated it becomes to keep track of things. So if I did lambda I minus A, the signs of everything off of the main diagonal would change, but you'd have the luxury, I suppose, of having lambda be the leading term in the values along the main diagonal. If that's something you find to be critically important, that's fine. It's just me personally, I like the knowledge that I don't have to worry about literally any values off the main diagonal. They're all going to stay exactly as they are. Just peace of mind. One less thing for me to forget. Like, driving halfway to campus today with my backseat filled with garbage. I mean, literally bags of garbage, because I drive the garbage to the dumpster. Except sometimes I forget to stop at the dumpster. So I am a forgetful kind of person. Literally, every time I'm the person that cooks in the house. Every night that I use the oven, I finish doing what I'm doing, start cleaning it up. Wife comes in. Did you mean to leave the oven on? Nope. Nope, I didn't. Like every single time. And I'm not even being funny about it. It's like it's just not something I can actually remember to do. But then I'll say something like, not in the moment because these are like fighting words, but I'll say something like, "Hey, did you mean to like miss a mortgage payment?" And if I time it right, it'll be it's like a touche moment. If not, it's a we're not speaking to each other for another 2 weeks kind of moment. So anyway, there's two ways to handle this. If I wanted to actually find the eigenvalues, one would be to actually diagonalize the matrix, but we haven't talked about that yet. And also, you need eigenvalues for that anyway, so or at least the eigenvalue approach. So what we're going to do is go through the process, like we did for the previous question, of determining what those eigenvalues are by finding where the determinant of a minus lambda I is indeed equal to 0. Right. So we're going to do a little bit of cofactor expansion along whatever row or column you want to work with. Zeros are friendly numbers, so wherever you can incorporate those, that's probably a good thing. So, if we were doing cross product, we'd have to work across the top row, but not the cross product. So let's work with something convenient. So I like row 2, I think. Wait, hold on. Let me see. Yeah, either way, if I do row 2 or row 3, I'm going to have these two guys in it, and so I'm going to need them. Yeah, I'll do row 2. And row 3. Yeah, reproduce the columns on the outside and go that way. Yeah, sure. Determinants was last unit, right? Yeah. Okay, good. All right, we've already been assessed on determinants, so it's not like you have to do it in any particular way. All right, so at this point, you do it whatever way makes sense to you.
Professor, were you saying that you deleted like the first 2 units of this class's YouTube videos?
No. Oh, okay. No, I kept them. I worked back from like the beginning of my account.
Oh, all right, yeah. No, because I was gonna say I was planning on using.
Yeah, that I wouldn't do that.
All right.
Yeah. So across the bottom row, I have a coefficient of 0. So then everything that follows that is going to be irrelevant. But I'll write the stuff that follows it just so I have it. And also, never hurts to have a little bit of review. -1, row 3, column 1. And then it would be multiplied by the matrix containing 1, 2, 3 minus lambda, 0. All right, but again, that goes to 0, so it's irrelevant. Plus coefficient 4, -1, row 3, column 2, matrix containing negative lambda, 2 to 0. That I think we can do pretty quickly. It's going to be -4. The determinant diagonal down is 0, diagonal up is 4. So 0 minus 4, so -4. And then the last one, the one where you actually earn your keep, purple, for those keeping score at home. Coefficient 5 minus lambda, -1, row 3, column 3, so that's going to go to 1 anyway. Matrix, negative lambda, 1, 2, 3 minus lambda. So we're looking at 5 minus lambda, diagonal down minus diagonal up. So diagonal down would be the product of the negative lambda and the 3 minus lambda. Distribute that because we're going to end up with a polynomial anyway. So that's going to be lambda squared minus 3 lambda. And then minus diagonal up. Which would be minus 2. And that whole shibiggity bangity boom should be equal to 0. But we'll get to that in a second. Okay, so little cleaning. I'm not sure how many of you like rational root theorem and synthetic division. I'll rephrase. I'm not sure how many of you know what rational root theorem is. Well, synthetic division you should know, right? It's like a division technique for polynomials. The rational root theorem is what you would do if you had a polynomial and you're like, I don't know what the factors are. I want to use synthetic division to get the factors, but I don't know where to start. So let me come up with a list of possibilities. The rational root theorem will give you the list of possibilities. It's the if I were to distribute this out, it would be the factors of the constant divided by the factors of the leading coefficient. So then you create that entire list, and using synthetic division, you go through the list, hoping that you get a remainder of 0, showing that it is in fact a root of the polynomial, leading to a factor if you wanted a factor form. That being said, it's not. I mean, it's linear algebra, but I mean, this I think might be the first instance where we're actually tempted to possibly do any kind of significant algebra. I suggest that you fight that urge and put it in your calculator, do a quick zoom 6, and see where it crosses the x-axis. All right. If you don't like that, go into the table, see where the y1s are equal to 0. All right. If you don't like that, put in a 0 for y2. Use your solver function, numeric solver. Y1 should be equal to y2. And where it says x equals, do an alpha enter to solve. It'll just shout out one of the solutions for you. And then just put in a different guess, like -10. You know, something in the positive neck of the woods, something in the negative neck of the woods. Alpha enter. Oh, it gave us the 6 again for some reason. The other one was 1 though, so that's weird how the 1's not showing up. Let me put in like a 0.5. Something close. If it drags me to 6, then I've done a good job of showing you why you should stay away from this approach. Yeah, so it's 1 and 6 based on, at minimum, the graph. Graph. It's a graph. So multiplicity of 2 at x equals 1 tells us that it's a double root. And a multiplicity of 1 at 6 tells us it's a single root. So we're looking at x minus 1, not that, x minus 1, I did it. I'm telling you guys not to write x, and I'm the one doing it. Lambda minus 1 squared, lambda minus 6 equals 0. All right, so lambda equals 1, 1, 6. All right, or just 1 and 6, but I'm just indicating the multiplicity component. More so for peace of mind, because when you see a polynomial with a degree of 3, you expect there to be 3 roots. So even when, I mean, this is just a me thing, I either whenever I solve a polynomial, and I like going all the way back to precalc, I'll either state the root twice, 1 and 1, or I'll say 1 mult 2, 1 with a multiplicity of 2, just so I know that I've accounted for all the degrees that make up the polynomial. All right. So anyway, we got our eigenvalues. Not asking for eigenvectors, so that's good. So I want the sum of my eigenvalues, so I want these guys. Quick notations, just you don't need the sub I if you don't want. The sum of the eigenvalues and the product of your eigenvalues. All right. The other reason why I indicate them individually, even if it's a double root, is because the sum of the eigenvalues should be equal to the trace of A. The trace of A is 8. If I forget to put one there, I would think that the sum of the eigenvalues is 7. It's really 8. The product of the eigenvalues is 6. So, I don't want to do it just because I feel like I'm getting carpal tunnel from using the mouse to type in matrices, but you can try it on your own. This is telling us that the determinant of matrix A is in fact equal to 6. Right. So we now know that we could actually determine some characteristics of our eigenvalues based off of the trace and the determinant of matrix A, right? Because, I mean, unless I just don't know how to do it, I don't think that there's an eigenvalue function in your calculator. Maybe there is. Maybe, I mean, there could be if you write a program, but I don't think there is. So we know that the sum of all of our eigenvalues is 8, and the product is 6. So, I mean, even if you did a little guess and check, you can come up with some possibilities. You could also try an approach where you solve it. You know, set up some equations. The issue, though, is you would somehow need to know how many eigenvalues there are, and that's something we'll talk about also. It's a fun little problem, right? That's kind of like, okay, so on a test, this question is either really involved and kind of annoying, or it's a gimme, based on whether or not you know this information. And it's open notes, so you better know the information, right?